Today we're going to take a look at logarithms, which, as many of you said, you have seen before. So hopefully this will be a quick little review for you. The plan is to just look at an introduction to them and their notation, what they are, and see if two different special logarithms, log base 10, ln, convert between exponential and logarithmic forms, briefly talk about the domain of these things, and then evaluate some very, very simple ones. So, struggling here. That's not the right page. First things first, why do we need logarithms? If you think of PEMDAS so far, so the order of operations, we have that multiplication and division undo each other, and addition and subtraction undo each other. And we've also seen how square roots can undo exponents, but they only undo exponents when you don't know the base and you do know the exponent. And what we actually need now is we need to see, well, what happens if I do know the base and I don't know the exponent and actually solve for the exponent? And those are for logarithms. So to undo or to solve exponential equations primarily, to find the value of an exponent. And there are logarithmic functions as well that are very important that we'll talk about, not all that long. And they can help model different phenomena as well. And how do we do this? Well, when we have an exponential equation of this form, I'm actually going to use different colors here. How about I even get rid of this so that I can start right away with nice colors? If I have some base to an exponent, and I want to solve for that exponent equals some other number, then what I can do is I can use an exponent or a logarithmic equation to solve that. So logarithms help us solve for exponents by saying, okay, the base, it's the same language, base A of B. And like I said, if we know the values of A and B, our calculator will help us do this. If the numbers are a little tricky, or just kind of thinking through various laws, we can get to what that value might be. So this is important. It is in your formula booklets, and you should become pretty comfortable with it, even without the formula, relatively quickly. There are a couple special logarithms, and they're special only in notation. They don't really work any differently. This log without a base is actually base 10 for our purposes. Log base 10. And that's because, like we saw scientific notation last time, it just is so important to look at the magnitude of things that we can use base 10. In other applications, you may see in computer sciences that it means log base 2. But for our purposes in the IB, if you see log base 10, it does mean, just log, it means log base 10. So you can either write it in or just imagine it there. That is fine. And the other important one is the natural logarithm. It's written in this order ln because French. I'm not going to try to pronounce it. It will be bad. And what that means is log base e. Base e. Some of you may have seen the number e, and some of you may be wondering, well, what is e? The number e is an irrational number, like pi in that sense. It goes on and on and forever. Here you can see what it is. And it has a ton of super practical and interesting applications. It is the base of the base rate of growth for continuously growing processes. Euler's number, that's why an e. If you're looking at compounding things, if you remember, and if you don't, that's fine. We're going to look at geometric progressions very shortly. If you remember, though, thinking back to like compound interest, you're dividing it by the number of times it's being compounded per year, for example, and then raising it to that. And if you make that go closer and closer to infinity, you approach this number. So also getting into limits, you'll see the same thing kind of written out that way. It has a really interesting property in calculus where if you're looking at the function y equals e to the x, the slope of that curve at any point is equal to the function itself, which is quite interesting. So e is a really cool number. Continuous growth, geometric growth, we'll take a look. And that's why it gets its own special logarithm. Again, ln means log base e. It does work the same way. If it helps you to write it out, go for it. Now, let's look at the kind of practical way we use this. Here's the formula again, not color-coded, write in logarithmic form. So remember that logarithms solve for exponents. So if I have log the base, the language is the same. The thing hanging off of the exponent is hanging off the logarithm. It is smaller. It's a subscript of 8 equals solving for the exponent. Same thing here. It is a little bit weird. It's telling us we're solving for the exponent. So here's the base, log base 12 of m equals the exponent. Do continue, we'll look at it further, but consider that if the exponent is a little bit more than just a variable or a number, so a whole expression like x plus 3, it's solving for the whole exponent. Writing in exponential form, we can look the other way. It's solving for the exponents. 3, the base hanging off the log is going to be hanging off the exponent, equals 27. Okay, z to the 4 equals 10. Okay, you can always just take a look and color code if needed. Important to note the domain of logarithms. It's okay if the value of a whole logarithmic expression is negative, positive, or 0. Those are, remember, values of exponents. So you can have negative exponents, you can have 0 exponents, you can have positive, you can have rational numbers. That's fine. What you can't have, not allowed, it's not possible to have a logarithm of a negative number. So that argument can't be 0, it can't be negative, because of, 1, it's a function, and 2, we just can't think of, for example, if it's solving for an exponent, there's no way to turn b to some number equals 0. Like, give an example, 3 to any exponent is not going to be 0. You can't take a negative exponent, a negative number, and raise it to something and get, the other way around. You can't take a positive one here, raise it to some exponent and get a negative number because of the way logarithms are functions, and we'll look more at that as well. So the argument has to be a positive number, cannot be 0, can't be negative. The whole value is fine. And now let's look at a few examples of logarithms here. Evaluating logarithms. To evaluate means find the value of. We're not solving anything, technically. So remember that this is actually solving for the exponent, saying it's asking us 2 to the what is 32. If I were to write it out here, maybe there's an invisible x or a box. What goes in this box? And that's saying 2 to what thing is 32. Okay, good. Well, really simple understanding this. 2, 4, 8, 16, 32. 2 to the 5th is 32. So the exponent I'm looking for is 5. Same thing here. Don't be careful what this is. It might help you to write it out this way again. 9 to the 3rd. Don't just assume that you see a bigger number there and a smaller number. We do have rational exponents and negative exponents. Is 3. This is not 3 to the what is 9. Important. Well, 9 to the half is 3. Remember, that's the square root of 9 is 3. So this is going to be a half. Slightly different because of square roots. You do have 2 different answers, but this is a function and it's not going to have 2 answers. We're just going to write the half. It's not going to be and negative half or whatever else. Okay, log base 10. Remember, this is an invisible base 10. So if I were to want to write this out, you can. You maybe don't have to. 10 to the what is 1 over 1,000. Remember that this 1,000 is, that's 10 to the 3rd. And to flip it, to create the reciprocal, it's a negative. So if I take negative 10, oops, that's not a 3, and I raise it to the negative 3rd, I will get 1/1000th. But about this one, well, remember that this is log base e of the square root of e. That's another way of writing that. You don't have to. So we're asking e to the what is equal to the square root of e. Remember that that's e to the half. So the question mark, the what is a half. Okay. A couple more tricky ones. Log base 5 to the negative 25. Remember, this is not possible, undefined. This is one of those domain problems because 5 to the what is negative 25. Well, nothing. There's no way to have an exponent that will turn that into a negative value. It's not negative 2. 5 to the negative 2 is 1 over 25. Okay. Pi to what is 1? Well, anything to the 0 is 1. This is actually a nice little property that's worth remembering. You don't have to. It's pretty easy to derive. Any base of 1 is 0 because anything to the 0 is 1. 16 to the what is a half. If I were to think through this and maybe write it out using those exponent laws we were looking at, 16 to the what is a half. Well, I do need to take the 4th root of it, and I need to make the reciprocal. So 16, the 4th root is going to be 1/4, and I want to flip it over, make the reciprocal, so negative 1/4. So lots of exponent laws. That's what a logarithm is, and we'll use logarithms to solve exponential equations in the near future.